Okay, so solving polynomial inequalities. So we have an inequality here. This polynomial is essentially greater than 0. That's what they've told us. Okay. The first step we go to figuring out at what points this will be greater than 0, or even helping for if we wanted to graph this, is finding out at what intervals will be greater than 0 in this case. Okay. So in other words, we need to factor. In order to factor this, because the type of question it is, we need to find a factor. So one of the ways we can do that is take the coefficient of the highest polynomial, or the highest variable term, and the constant at the end. If we multiply these two, we'll get a multiple. And then we find all possible factors of this multiple, and we test them by putting them into this equation. These are all the possible factors, right? So we have 1, 2, 3, 4, 5, 6, 7, 8 different terms we can plug into this polynomial to find out when it essentially equals 0. Okay, so we're going to switch this. We're going to say when it equals 0 in this case, because that's going to help us with the factoring of this. So if we plug 0 in, we know that doesn't work, and it's also not a function. So the very first one we can try is our number 1. So 2, 1, plus 3 to the power, or sorry, when x is 1, minus 17, that's supposed to be an x, isn't it? Yeah. Okay, 17 times 1 plus 12. We need it to equal 0 in order to factor. So this would give us 2 plus 3 minus 17 plus 12 is equal to 0. Let's find this out. 2 plus 3 is 5, plus 12 is 15, negative 17 plus 17 ends up being 0. Okay, so in this case, 1 is a factor. So we can use our synthetic division if we want to solve this. So if our factors are 1, we'll walk through synthetic division together here.
Wait, isn't it? Oh, never mind. Never mind.
You okay?
Yeah.
Okay. So we're going to write down the coefficients of each. So we have a 2, we have a 3, we have negative 17, and we have 12. Okay? So do you remember how to do this?
Yeah.
Okay, so let's go through this together. Tell me what the first step is here.
Bring the 2 down.
Okay. What do we multiply by?
1 and 2.
1 by 2. So we take the 1 and we multiply it by the 2. What do we get?
2.
Okay. And then what?
3 times 2.
And what does that give us?
6.
Okay.
I mean, no, you add it.
Okay. Good.
5.
So we add these two terms and we end up with our term 5. Then what do we do?
5 times 1, 5.
Okay. So 1 times 5, that gives us our 5.
And negative 17 minus, no, plus 5.
Yeah. What do we get?
30?
It's actually going to be 12.
Well, oh, okay.
Or negative 12, sorry, in this case. Okay. Then we do what?
Negative 12 times 1.
Okay. We multiply that again. And we get our term of negative 12. And what do we do?
0.
We add them and we end up with our term 0. Okay. So what does that mean? How can I write this as a polynomial now? How has that helped us?
Right.
How has that helped us? How do these numbers, how can we rewrite this equation?
2x.
Okay, so 2x.
1 less power than the first one.
Okay, good. So what was the first one we'd started with?
So 2x2.
Yeah, because we were at the power of 3. Okay, 2x2.
And plus 3x.
Plus, is it 3?
I mean, 5.
Yeah, our next term is 5. Okay, 5x.
Minus 12.
Okay, is that it?
No.
What's the times? What do we... There should be another bracket because we factored something out.
Oh, x.
Yeah.
Minus 1.
That's right. Because we used the term 1 here, because we had a value of 1, we need a bracket that essentially creates a 1, and x minus 1 when equal to 0. When you bring the 1 over, it becomes positive 1. So that's when x would be 1. Okay. So we can then go through, well, we now have a quadratic function. So we can just try to factor this. Do you remember how to factor?
Quadratic formula.
Mm-hmm. Oh, okay, yeah, we can use quadratic formula. We'll talk about it here. There might be a much faster way.
AC value.
Yeah, we might be using AC values. Okay. I think you guys do like decomposition probably. One way you can do it is find the factors of the first term and the last term. 12, 2, 6, 3, and 4. And when I multiply columns together, they got to add up to 5. So if I quickly look at this, What I mean by that is 6, 4, no, 4, no. What can I try here? So the way we do this method is I kind of do a trial and error. 2x times 1 gives me 2x, 1x times 12 gives me 12. That combination doesn't make 5x. I could go across, but that's going to give me 24 and 1. That won't work. So I know this column is a dud. Okay. Have you seen this method before? No. Another way you could do it is we try again 2x times 2, 1x times 6. So that gives me 4x and 6x. None of those add up to, sorry, that should be reading 5x. Okay, so going across didn't work. So now I go switch it. That would give me 12 and 4x. No combination of that gives me 5. So I know this column is a dud. So that means that I must be working with, these are my first terms and these must be my last terms, but I just got to double check. 2 times 3 gives me 6x, 1 times 4 gives me 4x. Well, that doesn't work. But if I go across, 2x times 4, 1x times 3, that'll give me 8x and 3x. Well, if the 3 is negative, this will add up to that. So I know these are the proper ones, or these are the terms I'm supposed to be using. So these will be my second terms in the brackets. These will be my first terms in the brackets. Okay? We go through that. We multiply, and we get 3x and 8x. Now, I know 3 needs to be negative in order for this to work, which makes sense because negative 3 times 4 gives us negative 12. So I know that works. So my factors, these are our first terms, 2x and 1x. And whatever we multiplied by, I got to put in opposite bracket. So because I multiplied 2x times 4, the 2x and the positive 4 go in opposite brackets, and then vice versa. Okay, and then we bring down our last one. There's many different ways of factoring. If you want to use quadratic, you could. This one tends to be a bit faster, especially when you get good at it. Okay, so we now have 3 terms here, and of course this is actually set equal to 0 in this question here. So what we found are we're going to be finding x-intercepts. When we set this equal to 0, we're looking for what our x-intercepts are. So if we split this equation, we can find out our 3 x-intercepts. 0 equals 2x minus 3, 0 equals x plus 4, and 0 equals x minus 1. Well, we know one of them will be x at 1, the other one's going to be x at negative 4, and finally the last one's going to actually be 3 over 2x. Okay, so these are our 3 points of intersection. Okay, what they've done in this question here is he says the x-intercepts are negative 4, 1, and 3 or 2. Those numbers divide into the domain of real numbers into 4 intervals. So they've given us 4 intervals here. And we're going to try to look at the bigger picture. You get the entire page. Okay, let's try to look at the bigger picture here. We can try to look at this by plugging these values into that original equation and kind of getting an idea of what we're going to end up with. Because remember, the inequality was greater than 0. Okay, so we need to kind of figure out in this question, is h at x greater than 0 when these things are happening? When x is less than 4, when x is between 4 and 1, or we'll organize that in a second. So you go down. Okay, I don't know where that was at. Okay, good. So let's try to put these on a number line. We have our number line here. We're going to figure out when is our function, I think we can call it f at x. When is this function greater than 0? That's what we need to figure out. Well, if we look at these on a number line, one point's at negative 4, another point's at 1, and another point's at 3 over 2, which is actually greater than 1. Okay, they're roughly that far away from each other on a number line. So there are 3 major intervals. Okay, we got to figure out when these hold true. So we'll kind of make it like lines, and we're looking at between these points. So is it possible that f at x is greater than 0 because it's an inequality when we're less than 4? That's the only option because there's nothing less than 4. So when x is less than negative 4, is that an option? There's the option here between these 2 intervals, which would be when x is less than 1, okay, but also greater than negative 4. That's another interval. The next interval is actually between these 2 points, because remember, these are x-intercepts, okay? So again, these 2 intervals being when x is greater than 1 but less than 3 over 2. And then finally, this interval here is when x is greater than 3 over 2. Okay? So we'll try to connect this to a graph a little so this makes sense for us. Scale of 1. Okay, so what they're saying here is because these are x-intercepts, right, at -4, at 1, and at 3 over 2, which is actually right there, we probably have some function that's maybe going like this, coming up, coming down, something like that, okay? We're trying to find when the function, or the y value, is greater than 0, okay? So that's our goal here. Well, to find out when this function is greater than 0, we kind of test these intervals, okay? We plug values that are less than -4, between -4 and 1, between 1 and 3.5, or sorry, 3 over 2, and greater than 3 over 2 into the original equation. The original equation they gave us, and we'll write over here on the side, what was it, 2x cubed plus 3x squared minus 17x plus 12. That was our original equation. We'll zoom in again, okay? So we're going to plug those values in to find out where it's coming from. Now, we can actually kind of infer where it's probably coming from. Do you remember working with cubic functions at all?
Like that one?
Yeah.
It's like,
Yeah, where a cubic function kind of looks like they usually, let's say, go like this. Do you remember this at all?
oh, yeah.
Okay. Now, is the a value on our cubic function positive or negative when it does that? Do you remember? Being the coefficient in front of the x cubed. For instance, this is also a cubic function. Do you know how to tell the difference between the two? Have you guys talked about it at all? No? Okay. So this can actually help us out quite a bit. Instead of having to put in the work, we can actually use this work as more of a verifying. But we'll let's put the work in first and then talk about the positive and negative intervals of a cubic function, because this is a cubic function. So one of the values that could be less than -4. Well, what can be less than -4? We can say when x is -5. We're going to use that to figure it out, okay? Because that would be less than 4. What's between these? Well, when x is 0, that's definitely between those values, right? Here's a little trick here. This is like when x is, you can put it as a fraction or a decimal. So I could say when x is, what is a good one to put? 4 over 3 would technically work. We could say 1.25. That falls because that's 1.5. So this is a possible option. And then greater than 3 over 2, well, that could just be x when it's 2, right? So we have 4 options to plug into the original equation to find out if f at x is positive or negative in these intervals. Okay, that was the whole goal. So we had to go through all the factoring to find this information. So we now go into it and we plug these into our equation. So I'm going to zoom in again so that we have a little more room to work. So we said our numbers were going to be, again, our equation is 2x cubed plus 3x squared minus 17x plus 12, right? Mm-hmm. First one we were going to do was when f at x was -5. So we're going to plug -5 in. Oh, sorry. Let's just say 2 times -5. Do you have a calculator with you? Okay, let's kind of try to do this all at one shot here. That's 12. Okay. -5 cubed is -125. Is that right?
Yeah.
Times 2 gives you -250?
Yeah.
Okay. 3 times -5 is -15. -17 times 5, 85?
Yeah.
Plus 12, okay. And you want to do this addition or subtraction here? We put these all together. I'm pretty sure we're going to get a negative term.
Yeah. -160.
Okay, -160. So in this case, f at x was what? Greater or less than 0?
Less than 0.
Less than 0. Now, so what that means is that this interval here, I went a little too far. At this interval here, we're actually less than. So we're not fulfilling this. This is not true for us, okay? So we're less than 0. So let's try another one at this interval here. So let's actually write our answer in here. We know that f at x is less than 0, Okay, so now let's find between -4 and 0. It's the same idea. We plug it into this equation. This one will be a little easier because when f is 0, I'm just going to write it straight in. That's going to be 2, 0 cubed plus 3, 0 squared minus 17 times 0 plus 12. Do you know what it's going to be? It's going to be 12 because 0 times all of these is 0 times 0. Is f at x greater than 0 there?
Yes.
It is. Okay, so f at x is greater than 0. We know that. So at this interval here, f at x is greater than 0. Now, this will be the tough one to figure out. We're going to have to take a look because sometimes things turns at critical interval points. Okay. Another point we found was 1.25, right? So we're going to need your calculator definitely for this one. We're going to plug that into our equation. 2 times 1.25 cubed 1.25 squared minus 17 times 1.25 plus 12. Okay?
I'm just going to put it all together.
Sure, yeah, do it all in one step. That'll be much easier for us.
Negative, do you want decimal?
Yeah, that's fine.
Decimal.
-0.65. Okay, we know it's negative. Important thing here is that f at x is less than 0 at this interval. And then the last one we were going to figure out when f is 2. So you want to try that also? Yeah. I'll write the equation down. And you just kind of give me the answer there when you type it in your calculator. That should be 8 times 2. 16. Should be a positive, whatever the answer is. Positive 6, is that what it is? Okay. 6. So f at x, again, is greater than 0. So, what we discovered here, let's go back to our intervals. I hate when that does that. Okay. Here, f at x was less than 0, and here f at x was greater than 0. Okay, so for this inequality. So we're going to get our answers in a second. I'm just going to quickly graph this and kind of make sense of it. Remember we talked about those being x-intercepts? Okay, well it said when we were less than 4, we were, f at x was less than 0, so we knew we were down here. Okay, and then between 4 and 1, -4 and 1, f at x was positive, right? F at x less than 0. From here to here, yeah, and I'm going to draw lines across this just so we're kind of getting the idea. These were our intervals. That one's kind of tight, but here f at x was greater than 0. So we know it does something like this. And then because it's negative down here, we know this is an x-intercept. It comes down, and then it comes up again, because here f at x was greater than 0 again. And then in this small area, f at x was less than 0, okay? And then they continue on like this, right? Again, this does represent a cubic function, and if we remember this here, the top value, this was a positive. Well, positive cubic functions start down here, come up, and end in a positive infinity direction. And if this had been negative, it would do the opposite. It would go down and go like this. So we know that what we found is true to what this function is, because this too is a positive function. It is going down, coming up, going down, and then going up forever. It's a proper cubic function, okay, from what we found. But the very question asked us, let's see it again. Okay, so this question is asking about ranges. When is it positive, right? When are we greater than 0? Well, we have to answer that within ranges. Well, we know that f at x is greater than 0 when x is less than 1 and greater than -4, and when x is greater than 3/2. Those are our answers. Those are when it's positive, okay? So quite a bit of work here. We had to do the factoring, then we had to kind of make sense of it with our graph there.